Welcome to RSET Online. In this session, we are going to deal with the topics of Module 4 of the course Cryptography and Cybersecurity from Semester 8 of Information Technology under KTU. We will be discussing cryptographic hash function, its properties, secure hash algorithms, message authentication code. Myself, Nikhila from Rajagiri School of Engineering and Technology. A hash function h accepts a variable length block of data m as input and produces a fixed size hash value, which could be represented as small h is equal to capital H of m, where capital H stands for the hash function and small h stands for the hash value. A good hash function has a property that the results of applying the function to a large set of input will produce outputs that are evenly distributed and apparently random. The principal objective of a hash function is data integrity. The kind of hash functions needed for security applications is referred to as cryptographic hash functions. The cryptographic hash functions should satisfy two main properties. First property is one-way property. That is, the hash value that is generated is not revertible. That is, you cannot generate the message from the hash value. Another property is the collision-free property. That is, no two messages should generate the same hash value. There are two groups of compression function. The compression functions are the heart of this hash functions. First one is the hash functions made from scratch, and the second one is the hash function made on block ciphers. And depending upon the type of compression function that is being used, we have got different classification of the hash functions, which is depicted in the slide. The figure represents the general operation of cryptographic hash function. The hash function h accepts a variable length message block which is converted to some fixed length and then padded with the values of the length of the original messages so that it becomes a fixed length block which is taken to the compression function h and generates a fixed length hash value. Now, let us look into the applications of cryptographic hash function. The first application that we are going to define is message authentication. Let's see what is message authentication. Message authentication is a mechanism or service used to verify the integrity of a message. Message authentication assures that data received are exactly as sent. That is, there is no modification, insertion, deletion, or replaying of the messages has been done during the transmit. In many cases, there is a requirement that the authentication mechanism should assure that the sender is valid. When a hash function is used to provide message authentication, the hash function value is often referred to as a message digest. The sender computes a hash value as a function of the bits in the message and transmits both the hash value and the message. The receiver performs the same hash calculation on the message bits and compares these values with the incoming hash value. If there is a mismatch, the receiver knows that the message has been altered. The hash value must be transmitted in a secure fashion. That is, the hash value must be protected so that if an adversary alters or replaces a message, it is not feasible for adversary to also alter the hash value to fool the receiver. Now, let us see the various ways in which the hash code can be used to provide message authentication. In the first scenario, you find the hash value from the message. The message and the hash value are being concatenated and encrypted using the key. The same key is used at the destination to decrypt the message, and you find the hash value from the message and compares the hash value with the hash value that is being received. And thus this provides, if both the hash value that is being received and that is being generated at the receiver are same, it provides that, or it ensures that the message is not being altered. Because only A and B shares a secret key, the message must have come from A and has not been altered. The hash code provides authentication, and because the encryption is applied on the entire message plus the hash code, it even provides the confidentiality. And let's move to the second picture. In the second picture, only the hash code is encrypted using symmetric encryption. This reduces the processing burden for those applications that do not require confidentiality. There are two more ways in which the hash code can be used for authentication. It is possible to use a hash function but no encryption for message authentication. The technique assumes that the two communicating parties shares a common secret value S. A computes the hash value over the concatenation of M and S and appends a resulting hash value to M. Because B possesses S, it can recompute the hash value to verify. As the secret value itself is not sent, an opponent cannot modify an intercepted message and cannot generate a false message. Now let's look into the figures D. Confidentiality can be appended or added to the approach of method C by encrypting the entire message plus the hash code. There is one more mechanism to ensure the authenticity using the hash code, and that method is called as a message authentication code. Message authentication code is also known as a keyed hash function, which is in detail discussed in the upcoming slides. Now, let us move to the second application of cryptographic hash function, that is digital signatures. In the case of digital signatures, the hash value of a message is encrypted with the user's private key. Anyone who knows the user's public key can verify the integrity of the message that is associated with the digital signature. Now let's move to the figure A. The hash code is encrypted using public key encryption with the sender's private key. This provides authentication. It also provides a digital signature because only the sender could have produced the encrypted hash code, because the hash code is encrypted using the sender's private key, which is the exclusive property of the sender. Now let's move to the figure B. If confidentiality as well as a digital signature is desired, then the message plus the private key encrypted hash code can be encrypted using a symmetric secret key. Now let us look into the other applications of cryptographic hash functions. Hash functions are commonly used to create one-way password file. In such schemes, the hash of the password is stored by an operating system rather than the password itself. Thus, the actual password is not retrievable by a hacker who gains access to the password file. Another application of the hash functions can be intrusion detection and virus detection. The files are being stored as hash value. One can later determine if a file has been modified by recomputing the hash value. An intruder who needs to change the file would have to change the file without changing the hash value. A cryptographic hash function can also be used to construct a pseudo-random number function or a pseudo-random number generator. A common application for a hash-based pseudo-random function is for the random generation of symmetric keys. Now let's look into the security requirements for cryptographic hash function. So before we go into the detail of the security requirements, we have to define two main terminologies. One is the pre-image, the other one is collision. Now let's look into what a pre-image is. For a hash value h is equal to h of x, we see that x is the pre-image of small h. That is, x is a data block whose hash value using the function capital H is h, that is small h. Because capital H is a many to one mapping, for any given hash value h, there will be generally multiple pre-images. A collision occurs if we have x is not equal to y and h of x is equal to h of y. That is, if two messages are having the same hash value, then we tell that there occurred a collision. Because we are using hash value for data integrity, collision are clearly undesirable. Let's look into the security requirements for cryptographic hash function. The first two security requirements are that is the hash function should take in a variable size input and it should be able to provide a fixed size output. The second requirement suggests that the hash function should be relatively simple. And the fourth one is the one which suggests the one-way property. That is, the hash value should be non-reversible. It is from the hash value, it should not be computationally feasible to produce the pre-image. And next one is, that is the fifth one, is weak collision resistant, and it tells that for any given block X, it is computationally infeasible to find out another block Y, which is where Y is not equal to X and h of X is equal to h of Y. And the second last property is collision resistant. That is, there should not be any pair xy such that h of x is equal to h of y. And last one is the output h should meet the pseudo-random test. There are two categories of attacks on hash functions. The first one is a brute force attack and the second one is a cryptanalysis. A brute force attack does not depend on the specific algorithm but depends on bit length. In the case of hash functions, a brute force attack depends only on the bit length of the hash value. A cryptanalysis, in contrast, is an attack based on the weakness in a particular cryptographic algorithm. Now let's look into the generic hash algorithm structure. The one which is depicted in the figure is referred to as the iterative hash function. We have already seen in the slide 1 on the starting slides that there are basically two types of hash functions. First one is based upon the iterative hash function, that is making the hash function from the scratch, and the second one is based upon the block ciphering. So this one is the iterative hash function which was proposed by Merkley and is the structure of and this is the structure of most of the hash functions that are being used today, including the SHA. The hash function takes as an input message and partitions it into L fixed size block, which is marked as Y0 to YL minus 1 in the figure, each of B bits. If necessary, the final block is padded to B bits. The final block also includes the values of the total length of the input to the hash function. Inclusion of the length is going to make the task of the opponent more difficult. The hash algorithm involves repeated use of compression function, which is depicted as F in the figure, that takes two inputs, an n bit input from the previous step, which is called as a chaining variable, and a b bit block, and produces an n bit output. At the start of the hashing, the chaining variable has an initial value that is specified as part of the algorithm. The final value of the chaining variable is the hash value. Often, B will be greater than N, and hence the term compression. We have to learn a hash function called as secure hash function, which is abbreviated as SHA. SHA has got different variants as given in the slide, which is SHA-1 to SHA-4, depending upon the size of the hash value that is being generated. SHA-512 is dealt in detail, where it takes the maximum message size of 2 raised to 128 minus 1 bits, and which in outputs 512-bit message digest, which accepts the message blocks as 1024-bit blocks and will have 80 rounds. Different variants of SHA and its maximum message size, block size, message digest size, number of rounds, word size, everything in detail is given in the next slide. There are basically 5 main steps for any SHA algorithm, that is secure hash algorithm. First step is appending padding bits, second one is append length, third is initialize hash buffer, processing messages of 1024 bits comes as the fourth step, and the fifth step is the final stage, this hash value. The algorithm takes as input a message with a maximum length of less than 2 raised to 128 bit and produces an output of 512 bit message digest. The input is processed as 1024 bit blocks, as you can see in the figure, and it processes the messages to produce a message digest of size 512 bits, and the initial value is which is represented as IB is of the size 512. The first step of any secure hash algorithm is append padding bits. Depending upon the version of SHA, the number of padding bits added keeps on changing. The message is padded so that its length is concurrent to 896 modulo 1024 in the case of SHA-512. Padding is always added even if the message is already of the desired length. Thus, the number of padding bits is in the range of 1 to 1024. The padding bits consist of single 1 bit followed by the necessary number of zeros. A block of 128 bits is appended to the message. 896, which is appended in the first step, along with this 124 bits in the second step, makes the last block of the size 1024 bits. The outcome of the first two steps yield a message that is an integer multiple of 1024 bits. Step 3 is Initialize hash buffer. A 512-bit buffer is used to hold intermediate and final result of the hash function. The buffer can be represented as 8 64-bit registers, which is being named as A, B, C, D, E, F, G, and H. These values are stored in big endian format, which is the most significant bytes of a word in the low address byte position. These words were obtained by taking the first 64 bits of the fractional parts of the square roots of the first 8 prime numbers. Now let's look into the step 4, process message in 1024 bits. As we have defined before, the messages that is given to SHA-512 will be divided into blocks of 1024 bits. Now how is this 1024 bits being processed? Using SHA-512 is what we have explained. Here we have got two figures, one in the right hand side which depicts as pointed in the slide, which depicts the entire 512 SHA-512 algorithm, and at the left hand side we have got the expansion of the function of SHA-512. It is this function that we are going to explain now, how each 1024 bit block is being processed by SHA compression function. To each function f, the input is the hash value of the previous step. That is why here the input h is marked as hi minus 1. That is the hash value of the previous step is given as the input for the next compression function. And each compression function has got 80 rounds, which is marked as round 0 to round 79. To each of these rounds, a 512-bit block is being 512-bit hash value is being passed through. And this 512-bit hash value is being mapped to the registers A to H, each of size 64-bit. The 1024 message block is being divided into words, the 79 different sets of words which is marked as 80 different set of words which is marked as W0 to W79, each of size 64 bit, and which is given to each round of each 80 rounds of the compression function. Along with the input message, here we have got one more input which is taken as the input for each round, which is marked as K0 to K79. Each round also makes use of the additive constant KT, indicates from one of the 80 rounds. These words represent the first 64 bit of the fractional parts of the cube root of first 80 prime numbers. The constant provides a randomized set of 64-bit pattern which should eliminate any irregularities in the input data. The output of the 80th round. So here we can see the output of the 80th round. It will be a 512-bit output, and this output of the 80th round is added with the output of hi minus 1. See here we are adding it up here. So it is added with the output of or it is added with the input of the first round of first round of this compression function or the output of the previous compression function. The addition is done independently for each of the 8 words in the buffer with each of the corresponding words in HI-1 using addition modulo 2 raised to 64. The last round of SHA-512 is step 5, that is the output round. After all n 1024-bit blocks have been processed, the output from the end stage is the 512-bit message digest. We can summarize the behavior of SHA-512 as follows. H0 is equal to initial value IB. Hi is equal to sum 64 of Hi minus 1 comma the registers of Hi, as we have defined in the previous slide. At the last round, that is after the 80th round of each compression function, the 512-bit output of the compression function is being added with the initial H value that is being supplied to the first step of the compression function, that is depicted using this equation, that is sum. There we do a 2 raised to 64 addition, modulo addition, that is Hi, that is what we have written it as. Hi is equal to, that is the hash value of the ith stage is equal to the modulo 2 raised to 26 addition of the hash value of the previous compression function with the hash value of the current compression function. Then MD is equal to, that is the message digest, is the hash value of the nth compression function. This figure depicts how the 512 bits of the hash value that is supplied to the registers A, B, C, D up to H is being processed before it passes from round 1 to round 2 and from round 2 to round 3 till it moves on to the round 79. So here, when the first registers A, B, C, D, E, F, G, H. The different operations are being performed on each 64-bit before it is being passed on to the next round, or before it is passed on to the registers of the next round. There are many operations which are done on these 64-bit using the word as well as the constant k. Next, we are going to define what message authentication codes or MAC codes are. Codes is almost similar to that of hash value. The only difference is that here this function is also a one-way function. Along with the hash value function, we have got a common key also. So this message authentication code can be used for both check the integrity of the message and to check the authenticity. And to check the integrity of the message, the receiver performs the same computation on the message and checks if the hash value that is being received and the hash value that is being generated at the receiving side is the same. And if it is same, then the message is not being encrypted. Sorry, if the message is not being modified. And to check the authenticity, as it involves a secret key that is being shared between the receiver and the sender, only if the message is being generated using the secret key, then it could only be the sender who has got the secret key to generate the message that has sent the message. Thus, it can ensure the authenticity of the message too. The security of the MAC depends on the underlying hash algorithm. There are three types of MAC. First one is the nested MAC, next is the HMAC and CMAC. We'll see the details in the upcoming slides. To improve the security of MAC, nested MACs were designed, in which hashing is done in two steps. In the first step, the key is concatenated with the message and is hashed to create an intermediate digest. In the second step, the key is concatenated with the intermediate digest to create the final digest. HMAC is another variant of the MAC codes. Here, there are different steps to be followed to form a HMAC code. First, append zeros to the left end of the key K to create a B-bit string, which is depicted as K plus over here. And if the K plus is not equal to 512 bit, then we append K plus with the iPad so that it becomes 512 bit, which is marked as SI, and this is appended with the message blocks, and this is given to the hash function, and you generate the hash function n bit hash function out of this message, and then this is taken as the input for the next round. In the next round also, key is appended with some values to form K plus, and it is added with some more bits which is called as a OPAD bit to make it of the size B bit. B is equal to 512 and it is named as S0. S0 is appended with the hash value and bit hash value, and this S0 along with the hash value is given to the hash function to generate the HMAC. The cipher-based message authentication code (CMAC) is a mode of operation for use with AES and EES. First, let us define the operation of CMAC when the message is an integer multiple n of the cipher block length b. For AES, b is equal to 128, that is the size of each block of the message, that is b is equal to 128 bit, and for EES, b is equal to 64. The message is divided into n blocks M1, M2, M3, Mn as shown in the figure, each of size 128 or 64 depending upon the encryption algorithm that is being used. The algorithm makes use of k-bit encryption key and b-bit constant. For AES, the key size k is 128, 192 or 256. For EES, the key size is 112, 168, etc. If the message is not an integer multiple of the cipher block length, then the final block is padded to the right with a 1 and many zeros as necessary so that the final block is also the length of B. In this session, we have gone through Module 4 of Cryptography and Cybersecurity from Semester 8. The topics that we have discussed here is the secure hash algorithm, that is SHA-512, and the requirement of hashing algorithms as well as MAC codes.